Welcome to this web lecture on transport and set theory. So throughout the last 2 web lectures, we've gained some basics in set theory, and now we're really going to move from those basics to what we need in our day-to-day life if we're working on transport. So just to rehash, we have a set of nodes which we refer to as A, and we also have an empty set which we denote by B. So now we have 2 subsets. One of them is G, which contains the elements 2 and 7, and one is the set E, which contains the nodes 1, 4, and 5. And now we would like to address any sort of combination of these sets, which is a concept that we know as the Cartesian product. So for instance, we would like to address 1, 2, 1, 7, 4, 4, 2, 4, 7, 5, 2, and 5, 7. Now the important part is here the order matters. So here 1, 2 is not the same as 2, 1. And the way that you can think of this is we would like to find all sort of ways that we can drive from set E to set G. Then of course it makes a difference if I'm driving from 1 to 2 or if I'm driving from 2 to 1. So this is why here we're actually also not denoting it by curly braces, but by these regular brackets, which means that here all of a sudden order matters. And this is what the Cartesian product is about. It tells us how we can combine 2 sets and then address all elements that are within. And this is what we denote by this E times G, so with this real X in here, which is then 1, 2, 1, 7, 4, 2, 4, 7, 5, 2, and 5, 7. That is the Cartesian product of E and G. You can think of, for instance, how things would differ if we looked at the Cartesian products of G and E. So now let's only look at the set G. We can of course also come up with the Cartesian product of G with itself. And this could, for instance, be the set of all arcs that are within G. So I can drive from 2 to 2. I can drive from 2 to 7. I can drive from 7 to 2. And I can drive from 7 to 7. But now let's look at all arcs in A. Actually, we don't have all road connections in here. So we don't have all options, which means that our set of all arcs that are actually allowed, the set B, is a subset of the set A, where A is A times A. So now let's only look at this subset G, and we see that there's 2 arcs that are actually going from within G to within G. And this is what we denote as E of G. So E is the set of all arcs which are in G, which is G times G, so the Cartesian product of G with itself, but then only those elements which are also in B, where B is then the set of all arcs. We can do the same with looking at the nodes with the arcs that leave the set G, so that go from a node that is in G to somewhere else. So for instance, this could be all roads that leave the city of Eindhoven. So, and this is what we denote by delta plus. So this is the set of all arcs that leave it. So this is the Cartesian product of G with everything that is not G, so A set minus G, but then of course only restricted to the arcs. So we're not going somewhere if there's not a direct connection. So we've seen delta plus. We of course also have delta minus, and delta minus is the set of arcs that go into the set G. So for instance, the roads that lead from outside of Eindhoven to Eindhoven. So this is the Cartesian product of everything that is not G, so A set minus G, multiplied with G, and then restricted to the arcs that we're actually having. Quite logically, quite often we would like to address both. So quite often we would like to address both the arcs that come in and the arcs that come out, so all roads that somehow connect Eindhoven to its surroundings. And that is something that we denote just by delta. So this is just all elements that are either in delta plus or in delta minus make up delta. So let's just say we're now only looking at this set at 2. 2 is of course not a set, it's a node. So now can we also do the same thing here? And with some slight abuse of notation within transport, we oftentimes say that delta of 2 is the same as delta of the set that contains 2. So here we're slightly overloading this notation, but of course it oftentimes makes it a little bit easier for us to address the arcs that leave a node versus the arcs that leave a set. So you always have to check a little bit, are we talking about a set or a node at this instance? So what I would like you to take away from this short web lecture is, first of all, what the Cartesian product is, and secondly, what the set of arcs is. Thanks.